Can you hear me, please?
Yes, sir. Yes, sir. You are audible,
Yeah.
sir. Sir, we will wait for 2 to 3 minutes, sir. The
Okay.
participants are joining again, and we will start the session at 7:30 p.m., sir.
Okay.
Right. Thank you, sir. Thank you. Subramanian, sir, shall we start? Hello.
Yes, we can start. Shall I share my presentation?
Just 1 second, sir. I will give you your brief introduction.
Okay.
Thank you, sir. Dr. K. Subramanian obtained his PhD from Cornell University in Electrical Engineering with a specialization in micro electromechanical systems, or commonly popular as MEMS. He holds BTech in Mechanical Engineering from IIT Madras. He is currently Senior Vice President at Ashok Leyland, where he leads advanced engineering and several other product development functions. Previously, he was the CEO and Executive Director of R&D at PowerGear Limited. He worked as a research center head at GES in New York. Subramanian has more than 60 issued patents as inventor in addition to numerous patents pending. He managed a large program on MEMS at GE and received two prestigious awards for his research. One of them is the Hull Award, among the top individual recognition at GE. The other award is Whitney Technical Achievement Award is for a market game changer project. He is also a Six Sigma Black Belt. He is a fellow of INAE and also a recipient of Lifetime Achievement Award in Engineering from Institution of Engineers. He mentors faculty, students, and startups in technology and business segments as well. Now, he is going to deliver on micro electromechanical systems for mechanical engineers. Thank you, sir. Over to you.
Can you hear me?
Yes, sir. Yes.
Great. I think I'll keep my video off because we are in presentation mode.
Okay, sir.
Yeah. Please let me know if you can see my screen as in presentation mode.
Yes, sir. Visible, sir.
Okay. So good evening, everyone, and thank you so much for joining late in the evening. But I promise we will make this next hour quite interesting. As the introduction happened, I am a graduate of IIT Madras in mechanical engineering about 30 years back. And I went to the US and I found this interesting new field of microelectromechanical systems, also called MEMS. It is called microsystems in Europe. And this was an up and coming area. So I understand that there will be a spectrum of people in the audience today. Some of you may know what it is. Some of you may have not been introduced to this topic before. But nevertheless, I hope there will be something in it for everybody. So with that in mind, feel free to interrupt if you don't follow or if you have any questions in between. That is fine. So I understand you're all muted, but please feel free to unmute yourself and raise a question anytime. So with that, let me get started. So MEMS is an acronym. It stands for Micro Electromechanical Systems. It is the technology of making mechanical parts on an extremely small size scale. So that is the first word, which is micro. Literally, the word micro stands for micron, which means it is 1,000th of a millimeter. It's a micrometer, which is 1,000th of a millimeter. So all of you know how small a millimeter is, but if you divide that into 1,000 parts and pick one part, it is a micrometer. And just to give you a size comparison, the human hair, the width, the thickness of the human hair is about 50 to 100 micrometers in size. So you're talking about sizes of the order of 1/50th to 100th the thickness of a human hair. Now that is the smallest feature in these mechanical systems. From there, you will be making mechanical systems on the size scale of 1 to 100, 200, 300 microns. But all of this is extremely small. And just to explain the other parts, electromechanical means that inside this chip you have primarily mechanical moving parts. So it's a chip that looks like a computer chip on the outside. But inside, if you look at it under a microscope, you will see largely mechanical moving parts. But to move them, you need electrical forces. Just like in a motor, to move a motor, you need electromagnetic forces. And for that reason, there is also an electrical angle to this. So it's an electromechanical system. Right? So you see two pictures on this slide. The picture on the top right is a device made by Analog Devices. Very interestingly, Analog Devices started launching products in the 1970s itself. So this is not exactly brand new technology, but there is so much new happening in this technology even today. What you're looking at that the person is holding in his finger is actually not the chip itself, it is the plastic package inside which the chip is there. So this is the plastic package, and you see on the gold colored terminals, which is the way to make connections. But the actual silicon chip is inside this, and it is significantly smaller than this. And to show you what is inside is the picture on the bottom right. So this is what is called a DLP, which is a digital light processor. It is also called a DMD, digital micro mirror device. This device was invented in the 90s, the decade of 90s. It actually took about a decade to invent it by Texas Instruments. And if you remember, sometime in 1990s or 2000s, projectors became extremely small and lightweight. That was because these chips were introduced into the projectors. And these chips are one of the technologies that are used in projectors, but it's quite a popular technology, and I'll explain how it works. So you see in the bottommost, you see a gold-colored thing, which is actually the chip. And what you're seeing on the bottom right, you have a funny-looking structure with many, many square structures. What you see on the bottom right is what is inside. It's a zoomed in view, actually from an electron microscope of what is inside this chip. And what is inside this chip is a lot of small squares, right? And that funny looking structure is actually the leg of an ant. So it is an ant's leg. It is just shown there purely for size comparison. You can even see the hair on the leg of the ant because it's an electron microscope picture. So actually the ant's leg is not part of the device. It is just shown there for comparison. But the actual device is the large array of all these squares that you see on that picture. Let me see if I can turn on a pointer. Yeah. So I hope you can see my pointer. So you have all of these squares, and each square is actually a mirror. I'll explain what it is actually doing. And underneath each mirror is a spring and a motor. So every mirror operates like a seesaw. It's just like the seesaw that is in the park that children use, where the mirror can be tilted one way or the other. And that is where the spring comes into play. If you tilt it and if you remove the power, then it will spring back to the position that is shown in the picture. So you can imagine a display that is made of this. Actually, this is a projector display. So what happens is the light, there is a bulb or an LED or something, which is shining light on this array of mirrors. And you can individually control every mirror to either shine that light towards the screen or tilt that mirror such that the light does not shine towards the screen, which means the light is pushed away from the screen. So just by tilting each mirror. Each mirror corresponds to 1 pixel on a projected screen. So you can imagine just by tilting the mirror, you can create a bright pixel on the screen. Of course, you have a lens in front of it. You can create a bright pixel or you can create a dark pixel if you don't send that light towards the screen. Right? So you can have an idea of how an image can be formed using something like this. So once again, you have a light bulb that is shining light on this array of mirrors. You have the control electronically from external to the chip through a circuit board, controlling the position of every mirror because there is a motor under every mirror. And the control is to either shine the light towards the screen or away from the screen, thereby creating a bright pixel on the screen or a dark pixel on the screen. And there are further techniques, which I won't go into now necessarily, to adjust levels of brightness of the pixels. I only spoke about bright and dark, but you can have different levels of brightness, shades of gray. You can have color. There are so many techniques to get to those, but we'll keep it simple. So you can imagine a typical projector screen where a projector is, let us say, displaying 1080p type image. And if you calculate how many pixels there are in a 1080p type of image, you will realize that it is 1920 by 1080. So horizontal direction it's 1920 and vertical direction it's 1080. So if you multiply, roughly if you do 2000 times 1000, you will have 2 million pixels on the screen. So 2 million pixels need to be refreshed at least 24 times a second. In many cases, it needs to be refreshed even higher rates. So these are mechanical devices that work extremely fast because you are talking about moving these mirrors on extremely high time scales. In fact, in reality, these motors behind the mirror actually move these mirrors at 100 kilohertz frequency, which means these mirrors are moving 100,000 times a second. And that is actually to create the brightness effect. How to have levels of brightness between fully bright and fully dark in a pixel. By adjusting the frequency, you can do that. So 100,000 times a second just to create one frame. And you can imagine how many times it actually moves over the life of the product. So you will realize that it actually, the reliability of this product is in the trillions of cycles. And these are numbers, trillion cycle reliability in terms of fatigue life in mechanical systems. These are numbers which are almost impossible in normal mechanical systems. And these numbers can be achieved because the material properties and the materials themselves that we use are actually quite perfect on this small size scale. So you can imagine that when you make extremely small sizes, you can get very close to single crystal type materials with very little defects. So any materials engineers in the audience will appreciate that. So the smaller you make a material, the probability that you have defects, actually you can bring it down through very careful processing. You can make materials that are almost perfect, and therefore the fatigue life of those materials is actually almost infinite, because when you talk about trillions and higher cycles, for all practical purposes, it's infinite. So I hope this gives you a flavor of. I wanted to start with applications. These are two applications. The one on the top is an accelerometer. I'm sure many of you may be familiar with accelerometers. Accelerometers are devices that measure acceleration. So any electronic chip is typically very good at logic and processing. It's a very good processor. But if you want to measure something in the outside world, that is a mechanical quantity like acceleration. Acceleration is a mechanical quantity. You will need a chip that is mechanical because it has to respond to a change from the outside world. So this chip that is shown on the top, which is the analog device's accelerometer, actually has a spring and a mass inside. And when there is an acceleration, that mass moves because it causes an inertial force. That moves, that how much it moves is proportional to the acceleration. And that how much it moves is converted to an electrical signal that you can read out. But at heart, the chip is still very mechanical. Right? So, and the one at the bottom is, of course, as I explained, a projector device. So, very different applications of micro mechanical systems. Any questions at this point? Okay. There are no questions. I'll keep moving. So this slide just shows you the size scale. On the top, on the left, you have an ant, which is about 5 millimeters in size. Then you are going progressively smaller. I told you human hair here, and then you're going to red blood cells and DNA and so on. And on the right, you have these devices, right? Just to show you the size scale comparison. So right across from human hair, you have these micromechanical devices. So these are actual pictures taken through an electron microscope on the chip. And these are what you're looking at is gears and some motors. And you can imagine the size scale is very similar to the human hair. Yeah. Right? And if you go a little even smaller, you get into the domain of nanotechnology, that which is not what we're talking about here. But a lot of nanotech and MEMS are also actually overlapping. So there's a lot of interrelated stuff. Okay. So why do you need to make something so small? I'm sure that question is there in almost anyone who is hearing this for the first time. We are taking a lot of trouble to ultra miniaturize mechanical systems. Actually, it is going to be very difficult to manufacture them when you do it and assemble them, right? So why take the trouble to do this? So there are so many reasons, and I'm just showing a snapshot of all these reasons. I'll go through this one by one because this is a very important slide for you to remember. First one is just miniaturization, because things are getting smaller and smaller. Look at your cell phone, it has sensors inside, and a sensor is something that needs to talk to the outside world. So it cannot just be an electronic chip. It also has to be a chip that is either mechanical or chemical or biological, depending on what it is sensing. So you need miniaturization. You can't build large mechanical systems to put into small devices. So miniaturization is an obvious reason why they do this. Second point is interesting. Lower cost due to mass or batch production. So this is the same revolution that happened in electronics. So if, in case some of you know how electronics is manufactured, it is made in a clean room. You have silicon wafers, and you batch, you print at a time a large batch of chips. So one silicon wafer may be several inches in diameter, but the chip itself is very small. So you put many chips on a wafer. Later you cut it out and then you package it. So in one shot, This is a printing technique. This is not like a lathe or milling machine type technique. It's a printing technique followed by deposition, etching, some electrochemical processes and all that, where you can literally batch produce or mass produce a lot of devices at once. What does that do? It lowers the cost. Just like electronics is now very cheap. In early days, electronics was made. It was more expensive, but now it is extremely cheap, largely because you take the largest wafer, silicon wafer you have, you put as many chips as possible on it, and then the cost of processing divided by the number of chips is the cost per chip. So that is happening, that revolution happened and is still happening with mechanical systems also. And mechanical systems, especially sensors or those actuators, which are those mirror chips that I showed you. So all of those can be fairly low cost. So imagine assembling 2 million mirrors and 2 million motors on a normal system, right? There's no way you can make it cheap. Only way to make it cheap is to use a semiconductor-like manufacturing process, which uses lithography, which is photographic exposure, followed by etching, deposition, etc., and use that technology to make mechanical devices. Third point, as assembled mechanical devices. So as you may have guessed, when you make parts that are so small, you cannot put it together. Assembly after you make the components is not at all easy. It's so small. So you may have seen watch assembly lines, which itself is a very intricate job. And you're talking now about parts which are much smaller than what a mechanical watch would use. So the only way to make it is to make it as assembled, which means there is no assembly step, which means that when you print it, for example, you want to mesh two gears together. You print the two gears in an already meshed condition, and therefore you don't have to assemble it later. Right? So the only option you have is, largely speaking, very, very occasionally they do some assembly, but largely speaking, they try to print all these, they just draw it in CAD in an assembled condition, therefore it will print like that. Fourth point, real world interface. I already mentioned this. So if any electronic chip is only good at processing, but you need a chip that is basically mechanical if you want to make a sensor. Because typically, if you're sensing pressure, if you're sensing pollution in the atmosphere, it's mechanical or chemical or some of those processes, right? So the chip has to be able to respond to them. The next point is extremely interesting: choice of exotic materials. Most of you, I imagine, are mechanical engineers, and you will know that when you actually practically make mechanical devices in the workshop, you use very few materials in the process. If you look at a periodic table has so many materials and therefore so much option in material properties. But you actually end up using a very small fraction of the table because everything else is expensive. You have to make your materials out of steel or aluminum, and you have choice of few more materials in coatings and all that. But that's it. But imagine if you're making something so small that now the cost is not an issue because you're only using such tiny amounts of the material. Then the whole periodic table opens up. Most of it opens up. Whatever you can process. Right? So you now get access to so many exotic materials. When I say exotic, I'm saying materials with all kinds of new properties. That for a designer, it's an amazing thing, because a designer who is in the conventional mechanical designer is restricted to conventional materials and coatings. Now all of a sudden they get access to so many different materials. In my own career, I have made micro mechanical devices, sometimes out of pure gold. Why? Because gold is a good conductor. So we needed that property. Gold is a noble metal. There is no corrosion that happens in gold. So we needed that property also. And the cost just did not matter because it's the amount used is extremely tiny. So we also made some devices out of materials like ruthenium, which you may never think of using in the conventional mechanical engineering. space. Right? So it opens up kind of materials that you can use. That is the other reason to go small. Next point, energy efficiency. Normally, if you make something very small, it consumes much less energy automatically because energy consumption is at to first order it is proportional to the mass of the moving object. And if the mass of the moving object is extremely small, you go from kilograms to not even grams, you go to micrograms. So orders and orders of magnitude reduction in mass. So therefore, you consume extremely small energies to move these mechanical systems. The next point, scaling of physical parameters. This is also very, very exciting, and this is probably the biggest point in the whole list. The same equations of physics that you use to do calculations for conventional mechanical systems, almost the same equations will apply for micromechanical systems also, except the numbers that you put into those equations will change. They will change significantly. So I'll give you a simple example. So just to write same equations of motion, but you're putting different numbers because you're putting smaller numbers, you're putting smaller mass, you're putting smaller size. So therefore, the output of that equation obviously will be a different number. You can take any equation, right? For example, you take the equation for frequency, which is omega is square root of k by m. So omega is resonance frequency, as you all know, square root of k by m. K is stiffness of the spring and m is mass. So it's a simple spring mass system where the spring has a stiffness k and there is a mass m hanging on it. So if you have a conventional mechanical system, you will make a spring and you will have a k value which is in Newton per meter. That is a unit of k, the stiffness. If you scale it down to the micro world, Newton per meter will become micronewton per micrometer. Why? Because you will generate very small forces, micronewton forces, and therefore you will get very small displacements, micrometer displacements. So the ratio will be micronewton per micrometer. So you can cancel the micros and you can make a fairly good assumption that the values of spring constant in the micro world are very comparable because the micros will cancel out, are very comparable to the values of large springs. The order of magnitude will be similar. But you have k by m. M will significantly change. K will not change. M will change significantly. So what M will do is you're going from kilograms to micrograms. So you're talking about orders of magnitude smaller mass. What will happen? Because M is in the denominator, the omega will be a much higher number for a micromechanical device compared to a conventional mechanical device, which means a small mechanical device, just because it is light, the mass is low, you can move it much faster. High frequency means you can move it much faster. So you can achieve speed in the micromechanical domain. Speed that is unheard of in conventional mechanics. In normal mechanical systems, you can make things move at 100 hertz, kilohertz, few kilohertz, right? Few kilohertz itself is fast, it's few thousand times a second. But in micromechanical, you can push it to megahertz. You can push it to 10, 100 megahertz. So you can imagine, right? Just one equation we took, we just put in same equation, but we put in different numbers, smaller numbers. And then the effect of that was that you can create these systems that move at phenomenal speed. And now, because if you remember, MEMS is electromechanical. You can, since you now have mechanical systems, just because they are small, they can move fast, you can actually make mechanical systems that operate on the same time scale as electronics. So you have a MOSFET in electronics, which switches in microseconds or even shorter. You can make a mechanical system that switches on the same time scale. So you are now operating in such a different domain, same laws of physics, but different numbers. I hope this is clear. Final point, harsh environments. When you make devices Electronics cannot survive in, for example, high temperature environments. Why? Because electronics has silicon and that is doped, and the dopants will diffuse, and therefore all these PN junctions will change. That problem is not there with mechanical devices. So you can push mechanical devices to significantly higher temperatures. So if you want a sensor that operates at, let's say, 200 degrees, 300 degrees, you can make it. It's almost impossible to do something like that with an electronic chip, right? And you can design a mechanical system for vibration, for shock, for all these other parasitic effects that may be required for the application. So any questions on this slide, or can I move on? Okay. So this slide is another application of MEMS. As I said, a lot of sensor applications are there. This one is a pressure sensor. And if you look at the photo on the bottom right, again, it's an electron micrograph. So it's not a photograph. Since it's taken through an electron microscope, it's called an electron micrograph. This has in the center, it has something like a membrane, like the head of a drum. Below this is vacuum or some known fixed pressure. Right? Don't worry about the holes for now. This is actually more like a microphone kind of application. But you can imagine a membrane with or without holes. And underneath is a fixed pressure. You can imagine vacuum. Vacuum is zero pressure. So when a pressure acts on the top surface of this membrane will bend. Just like when you press on the head of a drum, like on the dangam, the head will bend. The membrane will bend. Right? It's a small bend, you don't see, but it will bend. And you have transducers which will measure how much this bends. It can be done through piezoresistors, where the stress and resistance are proportional. It can be done through capacitance. When the gap between two surfaces changes, the capacitance changes. There are so many principles where a mechanical movement will create an electrical change. So piezoresistors is one example, capacitors is another example. So it's a simple principle. All you have is a membrane. Underneath is a known pressure. So if you have a pressure acts on top, it will bend, and the bend, how much it bends is given as a readout. Electronics will convert it to an equivalent pressure reading through calibration. Very simple device. So many types of pressure sensors are there. There are absolute pressure sensors. There are something called gauge pressure sensors. There are differential pressure sensors, and there are pressure sensors that work in extreme environments. All kinds of pressure sensors. And this one, with picture you're seeing on the top, is a tire pressure sensor, where if you want to know the pressure of the tire in your vehicle, why? Because this is actually a big safety requirement. You will never forget to fill petrol or diesel, but you may forget to fill the air in your tire. And therefore, if you have a sensor and if you have a display on your vehicle dashboard telling you what is the pressure in each tire, then it will alert you if the pressure in one or more tires drops to more than some threshold value, and therefore you can refill. And that's actually a safety issue. If you're driving on highways and all that, if the pressure is not correct, your tires could burst and you could have an accident. So this could be a lifesaver technology. So this is another very interesting application. This key-like structure you're seeing is just the packaging. The chip is inside. And this is just a packaging that allows you to add this sensor into the tire itself. So just another application. So here is, again, a whole bunch of electron micrographs which show you this as assembled structures concept. So this, even especially if you see this picture on the bottom left, is a rack and pinion here. And this is not assembled. This is printed in this assembled condition. Therefore, when it comes out of the manufacturing process, it already looks like this. So there is no assembly required. What you see on the top is a much bigger structure. So you have here you have a round gear with teeth, and here you have a straight gear with teeth. Also looks like a rack and pinion. And this part, which looks like these funny intersecting lines or overlapping lines, is actually a motor. So this is a motor that works on electrostatic actuation. It is not electromagnetic like conventional motors. It is simply a capacitor. When you have two plates like you have in a capacitor, and if you apply voltage, then you have equal and opposite charges that develop on each plate. And when you have equal and opposite charges, there is an attraction because you have plus on one side and minus on one side, so there will naturally be an attraction. And if you allow one of those plates to move freely and fix the other plate, then you have something that converts a voltage to motion. And that is a motor. And here you have a whole array of capacitors which adds up and gives a higher force compared to just one capacitor. So there are so many ways to rethink how to convert electrical to mechanical energy, especially when you go very small, because capacitance, you may remember, is epsilon A by D. So D is in the denominator, D is the gap between the plates. And if you can make that D extremely small, and here you can make it on this size scale of microns, then you can generate very high capacitances as a result of that, and therefore a lot of force to move these things. Right? Okay. I'm going to try to show a video. I think the organizers can tell me if it is actually working. Just give me 1 second. Can you see the video? Can someone just? I'm just pausing it. Is the video playing?
Yes, sir.
It's not playing.
Can someone speak up, please?
Yes, sir, it is playing.
Okay, thank you.
Hello, sir. Now it is playing, sir.
Hello, sir.
Yes?
Does the video have any sound, sir?
Yes, sound is not coming?
Yes, sir. Sound not coming, sir. Only video is displaying.
Okay, I don't know how to make the sound come. Let me, anybody has any ideas on Google Meet how to make the sound come? Let me see. Does anybody in the audience know how to make sound? Okay, I have no idea. I don't want to waste time now.
Okay, sir. Please continue.
Let me just play the video for just 1 or 2 minutes, and people can just see the moving mechanical devices, and then I'll move to the next slide. Okay, I'll stop the video here and I continue the presentation. Okay, so I think you saw some, hopefully you saw some examples. You saw the airbag, which is a safety device in automobiles today. The airbag is like a balloon. And in the video, if you noticed, when there was a crash, the balloon inflated from the mid-center of the steering wheel, thereby preventing impact for the driver. Because in a crash, the driver comes forward and hits the steering wheel, and this balloon comes and prevents the impact. So how do you know there is a crash? You have to use an accelerometer. Accelerometer measures acceleration, and here in this case it is deceleration because it's going from a high speed to zero speed in a very short time. Therefore, the deceleration, which is basically a negative acceleration, is measured by the accelerometer. And when that number crosses a certain threshold, obviously when you're braking also you will have deceleration, but when that number crosses a certain threshold, you have the trigger that you send to inflate. There's a small pump that very quickly inflates the balloon. All this happens extremely fast. And you saw even inkjet printers, which many of you may not have realized is actually a MEMS device, because the print head, which has micro nozzles for each color of ink, and it has these micro pumps which pump the ink out, which spray the ink out of these micro nozzles, and therefore getting ink out of the print head onto the paper. So inkjet print heads we all take for granted, but it's actually a MEMS device, which is another very interesting fact. So let me keep moving on this. So this is how it is made, and some of you may have already worked in a clean room, you may know this, but for the people who don't, there are actually multiple techniques. This is one technique where it's a combination of different processes. On the left side, you have a silicon substrate. I can just get the pointer again. Yeah. So you have a silicon substrate, which is actual the carrier on which you build these devices. And there are many different materials that you can deposit. So like here you're seeing a purple layer, which can be silicon nitride, silicon dioxide, it can be a metal, it can be some other material. So one aspect of making this is deposition, putting a new material on top of the substrate. Second one is masking. So when you put a new material, it coats the entire surface. This is the top view. What you saw on the left is a cross section. So what you're seeing in the middle is a top view. Whatever you coat, whatever material you put is there everywhere. So you have to form a shape out of it. So what you do is you photographically, you put an equivalent of a photographic film on top of this, and you expose just these areas in the photographic film. Here it is an eye shape, just to demonstrate. And when you expose that and then you develop it, then you can wash off the material in the other areas. So there are photographic processes used to convert a uniform layer to some kind of a shape. And there is, of course, etching, where you selectively remove some material. And there are many types of etching. You can just simply dip it in a beaker in a chemical, and that chemical will be a certain chemical that attacks one material and does not attack certain other materials. So you can selectively remove certain materials. Or there are other forms of etching using plasma, radio frequency plasma, where you put it inside a chamber, which is brought to low pressure using a vacuum pump, and there are some gases that are introduced, and they are ionized to form a plasma. The plasma bombards some of these materials to etch them. So you can add material, you can form shapes, you can remove material. So through a combination of these three major steps, you can typically form mechanical structures, except there is actually one interesting thing. So if you look at this cross section on this picture, you have a sequence of just 4 steps. First, you put this yellow material, doesn't matter what it is. And then second, you photographically expose certain parts and you etch, which means you're just removing that yellow material in certain areas. And then you put this red material on top, which actually is going to become your mechanical structural material. Right? And you remember, you can see that some of this is actually removed on this side and the right side, which is not, there is an intermediate missing step, which means you have another photographic exposure to remove some of the material on the extreme left and on the extreme right. And then there is another etching step, which is called a release process. which is very important because this has to become a freestanding mechanical structure. So in this case, you're looking at a cross-section of a cantilever beam that is made on a chip. And obviously all this is in microns in size. So here, you put it into, dip it, let's say, into a chemical that has the ability to react with this yellow material and then therefore remove it. So all the yellow is gone in the final figure. So all you're left with was the red material, which forms the cantilever. So cantilever is like a diving board. It's a simply supported beam where it's supported on one end and it's free on the other end, as all mechanical engineers know. So if you want to make a cantilever beam that can move up and down, so the whole point is to make something that can move. And just give me one second. Ma. Yeah, so there are many techniques like this to make MEMS devices. I'm just showing you one of these in the interest of time. So let's keep going, right? So I'll just skip some slides. Yeah. So this is a slide on the electromechanical part. I'm just talking about capacitance here. And as I briefly mentioned some time ago, capacitors are very interesting devices that can be used in sensors or they can be used in actuators, which is motors, to move something. So in the first picture, you're looking at, let's get the pointer. This picture, you're just looking at a normal capacitor, which is two plates, parallel plate capacitor, two plates separated by a distance d. And you're looking at a capacitor that is slightly offset. So there is a common area which is shown by the gray part, which is actually the area that matters, and the yellow part that is outside the area actually doesn't matter, right? And then you can also have a dielectric inside the capacitor. But here, because we want to ideally use the capacitor to move things, we usually leave the gap free so that these plates can actually move. And you can even have, like is shown in the right picture, you can have plates side by side. You don't actually have to have parallel plates facing each other, which is actually ideal. But even if you have plates side by side, there will be field lines that run from one plate to another, that is just shown by the curvy lines. And when you have this, you will have equal and opposite charges on this kind of a configuration as well. So why am I talking about this? If you look at the equation of a capacitor, it's C is equal to epsilon A by D. Epsilon, of course, has two parts. One is the permittivity of vacuum, which is epsilon naught, and the epsilon R is the relative permittivity of the material, the blue color material that is inside, if you have it. Right? But if you look at this equation, A is there and D is there, both of which are mechanical parameters. So capacitance is an electrical parameter on the left side, but on the right side, you have area, gap, and all that, which are dimensions, which are mechanical parameters. In other words, if you have a sensor where some quantity that you're sensing is either changing the gap or changing the area, you can measure it. It's called a transducer. So you can convert the mechanical change in area or distance to a capacitance change, which is an electrical change. Right? So this is a very powerful thing. So in MEMS, we always look for equations where you have an electrical quantity, but it's related to mechanical quantities. So if something mechanical changes, then something electrical also changes. Right? So obviously, if you look at the graph on the bottom here, if you change D, you have a nonlinear effect, right? Because it's in the denominator. So you have a sensor. You can change the distance. You can measure the change in distance through change in capacitance, but it's nonlinear. But if you change the area, you can actually have a linear effect because area is in the numerator. So this is just an example of how something as simple as capacitance can be used for sensing movement. And like you saw in the pressure sensor, if you move a membrane, the membrane versus another electrode can actually cause a change in capacitance. So these are various types of sensors that use capacitors. And all of you know that we all use touch, which is again a capacitive effect that actually doesn't move anything inside. But again, just to show you that capacitance is used in a lot of cases for actually sensing things. And you can either use direct change in capacitance, or you can have a circuit like this, which has an RC circuit, and you have an oscillator, and you can use changes in frequencies for more precise changes in capacitance. Okay, and this is another illustration of a pressure sensor where you're looking at the actual cross section of a pressure sensor, and you're looking at these pressure sensitive beam, and often in pressure sensors you have temperature compensation, because if temperature changes and the membrane that you're using to measure pressure actually expands or contracts because of temperature, that may look like a change in pressure, and that will give you a spurious reading. Even if pressure doesn't change, and if temperature changes, you will get a reading which looks like a change in pressure. So to avoid that, people have another mechanical device which will also change based on temperature, and you can take the difference and you can use the difference to indicate pressure. So this on the picture on the right is again an illustration of a capacitive pressure sensor, where you have this diaphragm or membrane on top, which is black in color, and then you have this fixed electrode on the bottom, and you're measuring capacitance between these two, and in between these two there is a gap where you hold vacuum. And vacuum is just zero pressure, so it's a very good reference for pressure. And when there is a pressure that is acting on the sensor from the top, what will happen is it will deform like this. The deformation is actually shown in a very exaggerated way. Deformation is usually very small, but since this gap itself is so small, you can even a small deformation can be detected using this technique. So this is actuation, right? So the same principle of a capacitor and what you're looking at in this picture to the right, the same principle can be used for actuation. So which means you can move things, you can create a motor, and you can use a simple capacitor, which is just two plates, one fixed plate. This is a fixed plate because it is anchored to something. The blue plate is a movable plate. Why? Because it is connected to a spring and it is freestanding. It can actually move. It is like the cantilever beam that you saw. And on the left, you just have an energy equation. So the energy of the capacitor is half CV squared. And if you differentiate energy, you can actually get force. I'll let you go through the calculation yourself. But the idea is that when you apply a voltage, which is shown through this voltage here, you will get equal and opposite charges and you will get an attraction. Normally a capacitor, both plates are fixed, but in here you are explicitly connecting one plate to a spring. Therefore, you're able to move this plate. So what you've achieved is without any magnetism, without any coils, you've achieved a motor. You've achieved the ability to move something just because it is freestanding and you have a force due to equal and opposite charges. So I hope this is clear. Okay, so I want to show a couple of videos, and hopefully since we are running out of time, it's almost 1 hour. What we did, I used to work at GE, General Electric, and many of you may have heard about GE. Many of you may have heard about GE. It is the company that was founded by Thomas Alva Edison when he invented the light bulb. And I used to work as a scientist in the US. So we made very small mechanical devices, and we used to use these devices for switching, which means we made mechanical relays as an alternative to electronic semiconductor switches. Why do we need to do that? Because semiconductor switches have a lot of resistance when they turn on. They still have, even today, the best MOSFETs have resistance in milliohms. But when you have a mechanical relay, when you turn on the switch, you have a metal-to-metal connection which has very low resistance. It's got resistance in microohms. So that's the reason that typically when you look at an power electronic circuit, you actually have a heat sink. Why? Because there is a resistance and therefore it's generating heat. And therefore you have to dissipate it. And that's not a very efficient thing. But a mechanical switcher, mechanical relay almost never has a heat sink because it is so efficient that the on-state loss when it's passing current is so small that it need not have a heatsink at all. So it's actually a much more efficient system. But there are issues with mechanical systems where until now it was not fast enough, it was not reliable enough. But with MEMS, we have the ability to make it extremely fast, extremely reliable. Right? I just showed you through that equation omega is equal to square root of k by m, how and why a mechanical system is very fast. And therefore, you can make a mechanical relay just by making it small, make it extremely fast. So I'll show you another video. Unfortunately, you won't have audio because we're not sure how to get audio on this. But let me see. Since this is playing from the PowerPoint, you can check if it's getting the audio. It's not playing. So let me try and give the audio commentary. So I hope you can see the video.
Yes, sir.
So what you're seeing here is the actual MEMS chip. I don't know if you can see my cursor, but you're seeing the very, very tiny chip. So in this video, you're going to demonstrate the speed of a very simple relay, which is a switching device. It's just a beam that goes back and forth. But we'll show you how it is extremely fast and something that you can't even imagine on a normal size scale. So we'll very quickly show you the picture under a microscope. So the MEMS switch is connected to an oscilloscope. You're seeing two waveforms. One of them is the actuation voltage, which is yellow, and the purple is the actual current. And this is the excitation frequency. He's starting at 300 hertz, which means he's switching 300 times a second. And he's now increased to 10 kilohertz, which means he's switching that switch, mechanical switch on and off 10,000 times every second. So what you're looking at is a slow motion camera. I'll just pause to explain this. So within this, you'll have to see, this is a small LED, which is going to be blinking when I turn the video on. So this has a switch, a micro switch that is connected to this. And that is 10,000 times a second. It is actually turning this LED on and off. But you can see it flashing because it is a slow motion camera. And it's being compared to a drop of water that's falling down. So I just turn this on. So this is another interesting experiment. This is a hot plate, so you can just adjust the temperature. On this hot plate, they've kept an aluminum tray which has some oil. They're going to put some popcorn on. They're going to pop that popcorn, which means that popcorn instantly almost pops, right? And then they are shooting this with a slow motion camera, and then they'll slow it down and show it to us. So they're putting that popcorn. It's an oil, and in just an instant, it will pop. Okay. So that corn has become popcorn, and now they will show the same scene in a slow motion effect, and they will compare it. You can see in this picture that the switch is actually running the LED on and off, and you can compare the time scale of a popcorn actually popping. So this is an amazing video, shows the speed of these mechanical devices. This is the actual switch which is connected under the microscope objective lens. You can see how just the green spot is telling you how very small that total switch is. All of this is made using MEMS technology. So I'll stop this video here and go back to the presentation. Yeah, so I want to stop here because I was told to stop speaking in about 1 hour. I'll hand it back to the organizers. You can tell me how to proceed. Shall we take questions or should we show a few more slides? You can tell me.
Sir, if you want to explain any few more concepts, please continue, sir.
Sorry?
Sir, if you want to explain any few more concepts, please continue, sir.
I think it'll be better to take questions because if I go to the next segment, it will be another half an hour.
Okay, okay. Thank you, sir. That was really, truly an excellent lecture, sir. Thank you very much. Dear participants, any few more questions? Participants, any questions from your end?
So I hope people are still on the call. If somebody asks some question, I'll at least know that you have understood something. Any comments? If you don't have questions, you can give comments also. Yeah, so Mr. Suresh, if there are no questions, we can close.
I think the participants don't have any questions, sir. Anyhow, thank you very much, sir, for accepting our request. We are excited by your biodata, and we are thrilled to learn the fundamentals of MEMS and their real-world engineering applications. Thank you very much, sir.
Yeah, if you have a 4-hour slot next time, I can give a more comprehensive talk on MEMS.
Sure, sir. Thank you, sir. We will plan.
Good starter. Yeah.
Because it was really a wonderful area, sir, for the next generation technologies. The MEMS are very, very, very good area, sir. So we will definitely plan next time, sir.
Yeah, and I have actually worked on it, spent many years on it, and I have actually taken it to product and commercialized.
But you have agreed our request even with a short notice. Thank you very much for that, sir.
Thank you. My pleasure. Yeah.
Thank you, sir. Dear participants, with this, the today's sessions are ended up. Tomorrow, the sessions starts at 2 p.m. Tomorrow, we have 3 sessions, followed by feedback, exam, and valedictory. So, the tomorrow session starts at 2 p.m. sharp. Thank you very much.